I'm back again.
Okay, it's done. Both
Okay, so now we are broadcasting
But we're 2 or
live.
3 minutes away, no?
Okay, yeah, 3 minutes to
Yeah.
We'll start, yeah, in 3 minutes like that.
How many people do we have? 24. Okay.
Yeah, I mean, you can hear me twice because I have that open, but it's closed now. So now we're broadcasting and everything is working well.
Good.
So the last timing of my lecture was like 21 minutes. I hope that's okay for Yossef.
Try to be a
This
bit.
is fine. Problem.
Well,
I
anyway,
don't know how
You
long
like,
mine
you
will
like
go.
to hear that, but not the organizers, maybe.
Anyway,
I'd like to hear you for 1 hour. It's okay.
this
You can
debate
take my
will
time
be very
too.
interesting because of the subject, because of the topic. So if you take a bit
Yeah.
more time, it's not real problem. No, there's no issue.
20 minutes, okay, yeah?
Yes, yes, yes.
Okay. That was okay.
There are many people joining the meeting now.
Okay,
We
good.
have
Yes.
around 30 some people, but there are many people entering now.
Okay,
So I will start in 1 minute. Okay.
Good.
okay.
זיו, תשים על מיוט בבקשה.
Best to wait for more to join, I guess.
Yeah, I'm silencing people when I found them, but
Yeah.
okay. So I think it's time for starting.
Okay.
So, dear rock mechanics colleague from Europe and the rest of the world, welcome to the third European rock mechanics debate. I am Leandro Alejano, ISRM VP for Europe, and I'm here to introduce this debate. European rock mechanics debates are based on an initiative by Charlie Lee, former ISRM VP for Europe, with the aim of get together from time to time and discuss hot topics on rock mechanics. These debates are held virtually, and each one will have two speakers with different perspectives on a hot rock engineering topic or on a specific technical aspect of rock mechanics. Both of them will present briefly their views and discuss with the other presenter and with the audience. One of the main aims is also to collect opinions and suggestions from the rock mechanics community. We start with the first debate on using hydraulic fracturing to measure in situ stresses with Gerkli and Marius Ryan in October 2021. Then we had the second debate entitled What Model for What Application in Rock Mechanics with Heinz Konietzki from Germany and Johnny Sjober from Sweden. And we have today the third debate on a very interesting topic, different approaches for tunneling, empirical, observational, and modeling approaches. And we have two excellent speakers, Nick Barton from Norway and Brazil, and Yossef Hatzor from Israel. both of them distinguished members of our society, so I'm really looking forward to listen to them. It's also fair to recognize that this debate would not have been possible without the tireless effort of Philippe Vaskou, who organized this and contacted the speakers, and will act today again as a moderator. So thank you very much, Philippe. Also, without the technical help for the webmaster of the ISRM, Ricardo Resende, and the ISRM Secretariat, this debate would not have been possible. In the same way, it would be meaningless to have this debate without your presence today. So thank you all for being here. And without further ado, I give the word to Philippe Vaskou, moderator of this debate. Please, Philippe.
Thank you, Leandro. So I'm Philippe Vaskou from France. And as you just said, Leandro, it took me not a long time, but some time to organize this debate. But really, I'm very happy and proud to present today two very famous ISRM members, Nick Barton and Yossef Hatzor. I thank in advance our two speakers for accepting to participate and debate on a very interesting and a bit controversial subject, the approach or the approaches to be used for tunneling works and stability purpose. Well, so the first presentation will be given by Nick Barton. Nick Barton is the inventor and developer of the Q system. So he is obviously the right person to present this empirical approach and the advantages when designing a tunnel. Nick developed the system in 1974, so now about 50 years ago. So the system has a very long experience and feedback. Nick has written many papers, several books on the subject. He's still extremely active and works as an international consultant. As compared to other empirical approaches, such the RMR or the GSI, the Q system is the one that allows a bit more real geological description of the rock masses and especially of the fractures. Also interesting is the input of the insider stresses, but I prefer to leave Nick speaking himself of his approach. So I'm going to share my screen and open.
So thank you very much, Philippe, for your introduction.
Please.
And also a little bit of bias from you. You are supporting Q also, so thank you for that. So we found that Philippe had to change the slides. We couldn't get a full screen with me. I think Microsoft are having some problems. So let's get stuck in. The empirical method for tunneling using the Q system. Don't go so fast as that. I hope you're not on a timer, right? The timer is off. Can you go back to the first slide? No, okay. So the site, we're using it for site characterization, day-to-day follow-up, and input for numerical modeling like UDEC BB. Yeah? Okay, next slide. So here you get the feeling you see Q system written so many times. Of course, I am biased, but it is the system I have the experience with because I don't use RMR or GSI. So we need a quantitative description of the rock mass, and we need for it to work within an empirical support method, if we can find one that's good enough, yeah. So by chance, I developed the Q system many years ago. It has a big numerical range, which is fundamentally correct. We'll see some pictures to demonstrate that. It has a proven case record, a track record, and it can be used on exposures when core logging day to day, and it gives simple tunnel and cavern support recommendations. Also, the relative tunneling cost and time are both related to Q. And Q or Q sub C, that's with the normalization with the UCS, they relate to the P wave velocity, the rock mass modulus, and actually to shear strength. So why not RMR or GSI? I think these have too small numerical scales, like 5 to 95. And I think they are both a bit poor on geology. That is my opinion. Especially they don't consider the number of joint sets specifically. Yeah? Next slide, please. So just for a little bit of organization, you'll see the first 16 slides is to do with characterization with photographs of Q examples. And then quite a lot about tunnel support components, including RRS and lattice girder critique. And then some of these Q links to cost and time and deformation delta and VP and EMAS. Sorry for the spelling mistake. And the last part, a very brief critique of Hook-Brown equations and continuum modeling. Next one, please. So in bridge design, basically one is using hopefully known materials, yeah? And in tunnel design, we have unknown materials, or it depends how well we investigate, how well they're known. And in both cases, we're using tangential stress and radial stress to make the bridge or the tunnel stable. And if the Q value is low, we need some help with the support, right? If the Q value is too low. This is a selection of nice photographs, but I and all of you maybe have thousands. It's basically to point out that we cannot test a rock mass sample as we do with steel or concrete or soil. So really the Q system saves us from impossible sizes of in situ rock mass testing. Next one, please. So with these thousands of photographs, hundreds of projects, many tunnels, and 40 countries so far and counting, one basic problem is that all the photographs and the rock masses, they're different. So we really need a day-to-day treatment. And next one, please. So this is a photograph that was not taken with the fisheye camera. It's just showing that there can be variation over short distances. We're in a granite quarry, not so far from Oslo, yeah? And the glaciation has removed in this area the weathering from the top surface, more or less. So all solutions are basically going to be approximate, yeah? So those of you who may not be familiar with the Q system, we use it down in the jointed area and another 1,000 or 2,000 meters below that. We leave the green and the orange for the soil mechanics people. So Q means rock mass quality or lack of quality, and there are ratings for 6 parameters that you see. And in pairs, they look like block size and interblock friction, something we call active stress. Next one. So just to see the full range of the Q value, the Sugarloaf Mountain in Rio on the left is maybe a Q close to 1,000 if we ignore that slab on the right side. And you see the parameters there, which give that number 1,000. On the right side, is a fault zone with swelling clay, and we're getting close to the lowest value there. So a range of 6 orders of magnitude, yeah? And I believe this wide numerical range of Q, it realistically reflects the huge potential differences in rock mass properties. If you think of modulus or shear strength or velocity or permeability, there's orders of magnitude changes, and Q or armor or GSI, they should really be reflecting that huge range. Next one. So surprisingly, the first 200 case records, when developing Q, they already included 50 rock types, a lesser number of sedimentary rocks. Next one, please. We now have many, many thousands of cases, I guess, especially due to the hard work of my colleague Øystein Grimstad in Norway. So here's this example of the first parameter, RQD. They are actually 4 distributions of RQD for 40 kilometers of core logging done by about 12 to 15 engineering geologists at a gold mine. And if we look at the Q equal 1 to 4, the bell-shaped curve, you see that that's a very nice demonstration of the usefulness of RQD in sort of setting the stage for moderately low, medium Q values that we call poor. So RQD has been used for 60 years, and I'm sure it will continue to be used. Next one, please. So here I've combined the second and third parameters, the number of joint sets JN and roughness JR. And in the red numbers at the bottom, you see ratios. And the red ratios, they would be conditions that generally don't cause overbreak. And the blue ratios, as in the photographs, they cause overbreak in general because of lack of roughness and too many joint sets. So when Jn over Jr is 6 or more, you more or less have an overbreak that's difficult to avoid, even with careful blasting. Next one. So we're still on the third parameter. This shows just a range of roughness getting more and more. And we're allowed to use JR of 3.5 if we think it's more than 3. Yeah, there's no problem there. So JR determines dilation angle, stability, overbreak, and even failure, of course, when the roughness is lacking. Next one, please. Here I've combined the third and fourth parameters, JR over JA. By a miracle, really, the case records on their own, they gave this ratio in numbers, and when you convert it to tan-1 JR over JA, it turned out to be like a friction angle. I had nothing to do with that, so to speak. The case records gave this all on their own. So that table there shows friction angles that one is familiar with. The top left may be phi plus I or phi plus dilation, and the bottom right may be phi with a contraction. Yeah. Next one, please. So Q is only part of the rock mass description exercise. You see on the right the 3 pairs of Q parameters. There are a lot of other parameters we will collect when we're describing a rock mass. And if we're going to do numerical modeling, quite a lot of those parameters in group 2, the joint character, they will be collected. On the left, you see a way of presenting a large number of Q parameter ratings for the RQD, JN, JR, JA, and so on. I will talk very little about JW and SRF. You just see glimpses of them. We've basically covered the first 4 parameters. Next one. So here, a little glimpse of Q with low UCS. Is that possible? In fact, this is the Channel Tunnel, and we're below the chalk cliffs of England in the left picture, just below the tide line, and some very distinctly linear joints, planar joints in the chalk marl. Chalk marl is only 3 or 4 or 5 MPa compression strength. And the small TBM tunnel, that is the first pilot tunnel, bored just about 1 kilometer in 1880 until the English realized the French troops could march through, so they stopped boring. And we had to wait 120 or 110 years for the channel tunnels, yeah, the pair, with a service tunnel in between. And the ruler there is showing also the planar joint sets subsea in a relief duct. And on the right, histogram logging of this very early tunnel, with a big range of properties during a few hundred meters. Next one. So now to support methods for tunnels, more about NMT, empirical, monitoring only with large spans. We don't need to monitor smaller tunnels because we know what the behavior is likely to be if we get the Q value right. We're not going to talk about NATM, but I will show 1 or 2 pictures. It's, I would say, semi-empirical, and we need careful monitoring. Next one, please. So thanks to a publication of NATM, AGS 2010, those are nice diagrams of NATM. We're not going to talk about that. We're going to concentrate on the left side. So if you go down those diagrams vertically, 1, 2, 3, 4. In 4, you see 2 gentlemen up in a cage, and they're inspecting the rock. They're seeing what the rock quality is likely to be on the next round. The bolt spacing there is exaggerated. Yeah, it's from a brochure that was made about 30 years ago. We'll see details of bolt spacing in a moment. Next one, please. So this is the support diagram that was developed by Grimster from lots and lots of case records. And if we go across lower down on the left, it's too difficult that I can't point, but I don't think you can see this arrow going 4, 5, 6, 7, the different thicknesses of shotcrete. And if we go in the top diagonal, you see the reducing spacing of the rock bolting as the Q value is getting less. And we can use this diagram for temporary support estimation by using 5Q 1.5 ESR. Next one, please. So here, photographs of the bolting and fiber reinforced shotcrete, which is preferred to bolting and mesh reinforced. The diagrams are very realistic, actually. They're from Van der Waal, 1990. And we also like the CT bolt with extra corrosion protection. There are still 4 layers of protection after a joint has moved and cracked the outer membrane, the outer grout, sorry. So the bolt is galvanized and epoxy painted. Then there's the inner annulus of grout and a PVC tube. So those are really permanent bolts. They cost a little bit more, but if you're relying on bolting and shotcreting for final support, that's important. Next one. So overbreak. This is, you could say on the left, a typical NATM tunnel. It has a final concrete lining, a drainage fleece membrane, and the overbreak has to be filled in one way or another, either with cheap shotcrete or with concrete. So the volumes of concrete are very different between the left and the right. This is a rail tunnel in Sweden where they were using the Q system, and there's absolutely no ring of shotcrete, but the rock mass is held extremely stably by a combination of rock bolts and shotcrete. We're not looking for a circular ideal shape to have support of the tunnels. We're helping the rock to help itself. That's the key principle. In a greater extent, I would say, than NATM, partly because most of the rock masses we're dealing with are a little bit better quality. Next one. So we may need to do pre-injection. These are some photographs from a 5 kilometer long tunnel, double track rail tunnel, where the grouting gave a very good result. And you can see the shotcreting, the rock bolting right up to the next blast to preserve the very good effect of the re-grouting. Next one. So when conditions are really bad, we're in where the blue arrow is in the Q support diagram. We use RRS, rib reinforced shotcrete arches. It's like a bolted lattice girder, but it's more flexible until it's bolted. And on the bottom left, you see photographs. They are 16 millimeter bars. We can slightly bend into a major overbreak. We're not relying on a perfectly circular LG or lattice girder. And they're sprayed in, and it gives an extremely stable condition where conditions are bad, and may be combined with spiling, as you see in the top left. Next one. So this is the best diagram to use for the dimensioning of RRS, thanks to the work of Grimstad and colleagues at NGI some years ago. And it's the left side of this little white boxes that gives you the area to get the design in the box. Next one. Here I'm contrasting the use of rock bolts and shotcrete, which gives very small deformation. You see in the top left diagram that is a monitored result from a test tunnel in mudstones. And the greatest deformation is with circular steel ribs. The deformation was getting more and more, and only when there was shotcrete added, the deformation was controlled. The lattice girders on the bottom right, they are actually looking very robust, 32 by 25 by 25 millimeter, but in fact they collapsed and folded completely when challenged by a very, very large vertical load that was an overburden of rock here that was not known. Next one, please. So some of the relationships between Q and other parameters. I published the results in the gridded figure on the top left, and some years later, 2 gentlemen from Taiwan, they sent me the results of hundreds of deformation measurements from tunnels in Taiwan on the bottom right. And it took me a while to realize the equation of the central diagonal is so simple as delta in millimeter equals span in meter divided by Q. The equation is so simple, it took a long time to really believe it, yeah, but it's true. But we have an improved version. The next slide. The second equation has span actually given in millimeter and a ratio of vertical stress and compression strength. So for cavern X and cavern Y, the simple equation gives 1 millimeter, 3 millimeter, and the more complex equation also gives 1 and 3 millimeter in this particular case. Next one, apply it to the Yossef cavern, and we get about 7 millimeter predicted. You see the 60,000 millimeter there in that red equation. And this is almost identical to the MPBX monitoring from 7 MPBX placed from the surface. And it's also identical to the UDEC BB modeling, which gave roughly 7 to 9 millimeter deformation. Next one. So my colleague Steinar Roald, some years ago, he collected data from 50 kilometers of tunnels, and he's represented here the relative time and the relative cost. So you see that there's a ratio 10 to 1 on time, that's the left diagram, and a ratio 12 to 1 on cost. So you get low costs when the rock qualities are really good. And as the Q value gets lower and lower, of course, the cost and the time increase enormously. Next one, please. Here I've slavishly used the Q system for arch and wall support for 3 different sizes of tunnels, small, medium, and a large motorway tunnel. And there you see the typical area of costs, relative costs for NMT in the bottom right, and the relative cost for NATM, because you end up with a concrete liner as some of those NMT case records would also require. We also use concrete lining if the quality is really bad. On the right, there are photographs from an NMT brochure from 30 years ago, yeah? And it shows a speciality really that we like the operator to be high up on the boom to do the best shotcreting, especially in big tunnels and caverns and slopes, of course. Next one, please. So Grimstar, again, he has compared Q and the cycle time. The cycle time is listed with all those words on the right. I won't read through them, but from a minimum of about 5 hours to increasing 10 hour, 15 hour as the Q value gets smaller and smaller, the cycle time gets larger and larger, yeah? Next one. We use Q to help with input data for numerical modeling. Here I'm showing the distribution of RQD down a borehole and the distribution of joints per meter down the same borehole. Q was varying similar to joints per meter, or around 2 to 30, mostly around 8 to 10 to 12, not increasing with depth, but velocity was increasing with depth due to stress. And that's the reason we have on the left, top left, we have the modulus 20, 30, and 40 GPa, yeah? You can see those numbers. Next one. So we can estimate a relationship from empiricism between the P-wave velocity from shallow refraction seismic, the scale on the top left, and the Q sub C scale, that's the Q value normalized by sigma C over 100. And those two equations in blue and black, they show how you can estimate the EMAS, the rock mass modulus, deformation modulus, as VP is increasing with depth, which it generally does, yeah? The depth dependence must not be ignored. Next one. To finally critique on almost the last 2 slides, I think, of some modern trends. Next one. So these extraordinary equations, I feel that they're extraordinary. They take such a long time to write unless you copy them. And amazingly, actually, the GSI effectively is appearing 16 times in the equation for C and 12 times in the equation for phi. And to me, GSI, although it's got geological in the name, it's not really geological, and it's not very easily quantified. And D is the disturbance factor. It's really a joker because you can get nearly any result by varying D from 0 to 1, yeah? Next one. So this these 2 figures, they're personal communication from Lisa Bakker when she was working in NGI in the same team as me. And I much prefer the discontinuum modeling than the continuum modeling, where one's getting much more information. Both those model methods are very nice models. They're both developed by Kundal, but the discontinuum modeling gives the best results, the most realistic results. Yeah. Next one. Finally, a historic picture, and we don't see any big wedges that have fallen out there from this 1880 rail tunnel. And I really question these wedge analyses with, I think, a lack of tangential clamping, yeah, and lack of dilation. So the final one, I think, is coming now. Next slide. So this is the end, and this is the same tunnel that you saw earlier with a very, very low inflow for 5 kilometers, and very high illusional range before the pre-injection. So pre-injection may be a very important part of NMT. And the last slide is 3 conclusions. Empirical-based design, in other words, selection of support classes, is urgently needed on a blast-by-blast basis. The rock mass is unknown. Q-system characterization for tunnel support selection is empirical, and therefore it works. And to me, GSI and Hook-Brown equations for rock masses are not empirical, and they're highly suspect as representations of the geology. So thank you for attention, and I'm sorry I've used perhaps a little bit more than 20 minutes.
Thank you, Nick.
Thank you, Philippe.
Now I have to introduce the second speaker, Yossef Hatzor. Yossef is professor at the Ben Gurion University in Israel. Sim's master and PhD thesis on discontinuous rock masses and validation of block theory under the supervision of Professor Goodman. Yossef Hatzor has always been working in the field of fractured rock masses, discontinuous deformation and engineering geology of tunnels, slopes, and reservoir rock mechanics. Thus, Yossef is what I call a real practitioner, adding strong theoretical basis to field observations and analysis. His last book was published in 2017 on discontinuous deformation analysis, DDA, in rock mechanics practice. And because of his very rich experience, Yossef Hatzor also acts as an international expert and consultant. Well, that's over to you, Yossef.
Oh, thank you very much, Philippe, for the kind introduction. And thank you, Nick, for this wonderful presentation. And I want to present an alternative view where the emphasis regarding the prediction of the deformation of the rock mass around the tunnel is on the discontinuities, as we see here in this wonderful photo that in fact was taken by Dr. Genhuashi in the Jinping project. So I'm going to present 4 cases that make us scratch the head and think what's going on and appreciate the need to consider the rock mass structure when we design excavations in rock. As you all know, rocks are discontinuous, and therefore, as also reflected in the Q system, the discontinuities play a major role. What I want to argue here is that the orientation of the discontinuities cannot be ignored. So I'll go through several case studies, starting with 2 tunnels in America. This is from my PhD work. And so in a sense, in a way, this presentation will go through my career, starting from the PhD work in the early 90s through some works in Israel in the 2000s, and then in China and between 2010 and now. So this is 2 tunnels that we used as case study to validate block theory, and that was just then published And together with Professor Goodman, we went to these tunnels and looked for evidence that block theory is indeed, it is able to predict failures in the rock. So 2 tunnels, one in Colorado, the other is in Tennessee, Glenwood Canyon and Cumberland Gap. And the work was published in a series of papers, as you can see there. So in Glenwood Canyon, they excavated this pilot tunnel. You can see that this pilot tunnel is within a wedge in the rock. And the rock mass turns out to have 7 joint sets. If you have 7 joint sets and you want to consider combinations of 3 joints in every block, you're going to end up with about 35 possible joint combinations. Now, that's not realistic. And why do I say 3? Because we often find in the field that the blocks are tetrahedral, meaning there's 3 joints intersecting at the point in the apex, and then there is the free surface. And the reason for this is that predominantly they are tetrahedral is because the probability to obtain 4 joints intersecting through the same point diminishes very rapidly to 0. Therefore, we always find tetrahedral blocks, and this is why we're going to have to analyze 35 different joint combinations. Now, in each one of these joint combinations, there are theoretically 8 possible joint pyramids. If you remember, if you don't know, if you're not familiar with block theory, so here is an example from Goodman's book. We have 3 joint sets, and their intersections form in space joint pyramids. Each one has its own code, and the Shear's removability theorem says that the removable JP is the one that is completely contained in the space pyramid, in the space. So we're going to have 35 theoretically removable JPs from every free face. That's too many. And that's when, in fact, I came up with the idea that they are not, the probability for the different joint intersections is not the same. And we came up with this concept of block failure likelihood. And in fact, there are two criteria for this. One is the joint intersection probability, and then there's the stability of the removable JP that is formed. So the joint intersection probability is simply inversely proportional to the volume of this parallel pipette. So the smaller the spacing, the higher the probability, makes it more often in the rock mass. And then we have to run through these occurrences, a limit equilibrium analysis to weigh the stability of each of these removable blocks and come up with the block failure likelihood. And I didn't alter those figures. They are from my work in the 90s with Professor Goodman. I kept it as it is, but you can see the survey from Hanging Lake Tunnel and from Cumberland Gap Tunnel, and we compare between the block failure likelihood, which is a number here, the way it was formulated back then, and the number of failures that were mapped in the walls as block molds, and you see that they match. So a lot of these theoretical combinations don't yield removable blocks that we need to be concerned of. And that means that with running such an analysis, it's not so complicated. We can actually define 1 or 2 blocks that would be critical for a given free face and design for it, study its maximum length, and then dimension our support accordingly. So this is the issue of the block failure likelihood. This is not something that can be done with conventional classification methods. I'm not distinguishing right now between the existing methods. The other thing I want to point out is that the deformation in the roof, not only it's a question of the rock mass quality as Nick proposed with his empirical equation span over Q. It's very interesting that he was able to validate that. But in fact, the interaction between the blocks in the roof play an important role. So this is just an example of an historic site. I spent a lot of time in my career working on preservation of ancient sites underground and on the ground, slopes, tunnels. And this is a Tzedekah cavern underneath the old city of Jerusalem. And it's been standing there for at least 2,000 years, probably more like 3,000 years, or anywhere between 2,000 and 3,000 years before present. Historians tell us that the dimension stones for the temple were quarried in that quarry of limestone. And within this quarry, we have a hall that has been called Freemasons' Hall, because the Freemasons make their initiation ceremonies there, used to at least. Anyways, it's a large span room that is standing unsupported for thousands of years. Mm-hmm. And the question is, why is it standing? How can it be stable for so many years? And if we run a clamped beam analysis on this layer of the roof, we get that the maximum tensile strength here should be about 10.5 megapascals. But the tensile strength of the rock is only 2.8 megapascals. So it must have, if this was the model, it must have failed in tension. If we go to Brady and Brown's book, where they discuss the voussoir analog, where you let those two blocks rotate a little bit, to divide the immediate roof to 2 blocks and let them rotate a little bit. And so you develop those compressive stresses here and here. Then there's 3 different kind of failure modes that could be happening. One is crushing under the maximum stress here. One is shear along the abutments. The third one is snap through mechanism buckling. And running this analysis on the Freemasons' Hall gives us the buckling failure mode, because the layers are thin and the span is large, and it didn't happen. It didn't happen. So both methods of analysis don't work. And this is my second point, is that we need to consider the interaction between the blocks. So here we have a mesh, a DDA mesh of many blocks. If you notice, by the way, the structure here is geological. It's not just drawing vertical lines and horizontal lines and cutting them, no. You can see that there is joints terminating against layers, cross joints and not crossing joints. So there, a lot of effort has been put in here to generate a mesh that will represent the sedimentary rock structure properly. And what's going on is that you can see the arching stresses developing around the hall. And then there is some shear developing along those 2 abutments. But then after some shear, there is an arrest of the motion and a development of arching stresses through the immediate roof. You can see it here. This is the vertical displacement. So if this is the lowermost layer measurement point, it goes down and then it stops. And that's when this horizontal stresses reach their maximum value and the displacement is arrested because of the arching mechanism. So I don't think we could have predicted this without applying a specific analysis that will consider the interaction between the blocks. And this is another issue that requires us to, after we have established the rock classification, we need to do this, of course. It requires us to go on further to more specific analysis, considering the interaction between blocks. The third case is from China, and this is the Baheitan project in China. It's a huge hydropower project. You can see this river, which is on the boundary between 2 provinces, between Sichuan and Yunnan provinces. And it's going to be 300 meters high. And the geology is tricky. We have a contact here between columnar jointed basalt and sandstones. And everything is going to be within the columnar jointed basalt. And you can see the columnar jointed basalt. You can see that it's anisotropic with prisms dipping into the tunnel. And how do we handle that? So again, we can draw a mesh. This photo just tells us where we put the measurement points in the mesh. We do sequence excavation in the model, remove the top heading and then the center part and then the bench, and we study the deformation after imposing the initial stresses. And you see that in this mesh that represents the mapping exactly as it is in the field and the initial stresses as were measured in the field, see that the three immediate points, 1, 2, 3 in the roof are all sliding down. So 9 meters above the roof, this is just one of the powerhouses on the way. So 9 meters above the roof, we see that the whole thing is sliding down. Now, the other measurement point, number 4, is at a distance of 25 meters from the roof, and it stops. So it doesn't slide. So somewhere between there, between 9 and 25 meters above the roof is where it stops to slide. So we need reinforcement that it will go beyond those 9 meters. Could have this been predicted without such an analysis? And moreover, you can see the deformation in the two side walls. In the right side wall, we get sliding, and it tells us where the sliding stops, the loosening zone. And in the left wall, we see rotation. You see, this is here the rotation angle in radians. So you see that point number 9 is actually rotating because of this structure that favors toppling. So the third point I want to make is that applying such an analysis gives us the failure modes that will develop around the tunnel. And to confirm this, you see that the MPBX measurements show that the maximum displacement in the roof is about 9 meters above the roof, and then it stops about at a distance of about 20, which is what we basically predicted, and the same with the side walls. Now, their approach to the support of this chamber was following T.A. Lang's guidelines for dimensioning rock bolt reinforcement. So they came up with a length of 6 meters, spacing of 1 meter. They did some longer lengths on the sides here, but basically the roof is these rock bolts here are 6 meter long only. And as we saw in the analysis before, it's not long enough. And the reason for this mistake is that they did not consider the structure of the rock, because T.A. Lang's guidelines take the average block size to scale the block length. And what I'm arguing here, that in the roof, the average block size would be the distance between those basalt layers of the flows of the basalt. So it would be about 5 meters. Then you need, if you go by the rule of 3B, you need at least 15 meters long bolts. And in the side walls, the length of the width of the block is very small, on 30 centimeters, the width of the columns of basalt. So we're going to go using the other criterion, which is about 1/4 of the span that gives us 5 meters. And then if they went with that kind of approach, it would have been safe. You can see that when we apply the bolts the way they designed it, nothing happens. Everything is sliding down because it's not long enough. And if we consider the anisotropy of the rock mass, and so that requires 15-meter length bolts of cables, I would say, in the roof, and about 5 meters length bolts in the sidewall, then they would have been safe. So that's my third point, the consideration of anisotropy. And finally, something that is in favor of classification methods. I use the GSI here, but I could have done it just as well with RMR or Q, so please don't attack me for using the GSI, but I'm going to show you that classification methods can be very useful. So this is the Jinping hydropower project. You probably all have heard of it, very, very big. So we have a dam here and 6 turbines of 600 megawatt each. Then we have 4 head race tunnels. So the difference in elevation between the riverbed here and here is 250 meters. So when you come, and then above you, you have 2,500 meters of the mountain Jinping. So very deep. And now, so here we drill the tunnels, they drill the tunnels through the mountain, and the water flows by gravity to Jinping 2. And then they're dropped inside the mountain to operate to turn another 8 turbines of 600 megawatt each. So they generate 6 times 600 on Jinping 1 and another 8 times 600 megawatt on Jinping 2. So it's a very green project. It's all hydroelectric. It's very, very nice. And it's all because of the bend in the Yalong River, which is in a branch of the Yangtze River. And and because of the difference in elevation between this point and this point. So what happened was that they encountered a lot of rock bursting while drilling, excavating those forehead raise tunnels and the drainage tunnels. A lot of rock bursting, a lot of delays and a lot of risk for the workers throughout the excavation. And the question was, can we predict this, the intensity of the bursting? So I collaborated here with a postdoc, He Ben-gu, now is in Northeastern University, together with Professor Feng Xiating. And he developed the analytical solution for the energy concentration. Okay, so the strain energy before tunneling, and then the energy concentration after removal of the tunnel. So we know the difference. And of course, for chilly material and so on. So what we find in his solution is that once you go beyond 3 diameters away from the center of the tunnel, it doesn't really matter anymore. So this is the affected zone of about 3 diameters. And if we want to consider jointing within this annulus that is mostly disturbed because of the tunneling, but now we have a tool to calculate the energy, this is very useful. When we consider discontinuities, we can say the following argument. We say that rock bolts, the rock bolts have been considered to be a process where the intact rock is being fractured, starting from the work of Professor Cook and Verhulst in South Africa. The work on the failure of the intact rock by stress concentrations on the sidewalls. But my argument is that if you have discontinuities, pre-existing discontinuities, and they're favorably oriented, then of course the shear strength of the discontinuities is lower than the strength or the shear strength of the intact rock. And then if they're favorably oriented, blocks will fly out much before the rock will fracture in compression or tension. And indeed, when they map it, they see that blocky rock masses generate most of the rock bursts, where intact massive rocks generate much fewer rock bursts, and disintegrated rock also doesn't generate too many. So that is the motivation. And now that we have this equation, we know that the increase in the annulus, that is the affected area, the increase of energy is 1.7 plus the original times the original energy. That has to be balanced by the elastic energy, the strain energy of the blocks, the kinetic energy of the blocks that move, and the shear energy that is being dissipated through shear. So that is the equilibrium of the energy. Now, when we only take the kinetic energy of all the blocks in this annulus following the excavation, which we can obtain because we have the velocity, for example, in the DDA model of each block at every time step, we can see that how the friction coefficient affects the kinetic energy that is being released. When friction coefficient is low, we have a lot of energy. And then as we increase the friction coefficient, the energy goes down. And for example, if we want to use this approach to study mitigation, we can say, if we go full phase, we're going to get a very strong seismic event. However, if we go top heading and bench, that if we just remove half the top heading, half the height, this is the first event, and this will be the second event. If we first remove third, we'll have a small event, but then we'll have a higher event when we remove the other 2/3. So we can use this kind of calculation. So what I wanted to say is that we can to study the risk, the rock burst risk, or to be able to predict the risk, we can consider the rock mass structure. Now, I did it with RMR in one work, and now I did it here, and I did it with GSI. I probably could have done it with Q as well. The reason I chose GSI here is because it has those nice illustrations of the rock mass structure, which I can use then to replicate in DDA. And how I do this, I invent numbers. I just out of my head, I say, okay, so GSI 50, all right, 4 joint sets. I'll give them some orientations. That will be the total number of blocks in the mesh. I will do this kind of spacing. Now, important thing I want to point out is that spacing is not the only parameter that is important. Also the length of the joints and the bridge between the joints. So you can see parameters here, because that's what is responsible for the interlocking. If we just generate long, infinitely long joints, we get an artificial mesh of lines that intersect one another, and the deformation pattern will not be realistic. But if we consider spacing, length, and bridge, then we are getting a more realistic, more geological, as Nick said, picture. And now I assign just friction angles for the different GSI values and the intact modulus from the rock mass modulus. So these are all my own guesses, okay? And so I can generate meshes that correspond to different GSIs. So this is GSI of 50, and this is GSI of 70, and this is GSI of 80. I'm using the statistical line generation code and then the block cutting code in the DDA mesh. And I'm getting these maps of rock mass structure. Just to show you, zoom in, this is a 55 GSI, and this is a 75. And everything is under initial hydrostatic stress of 50 and 55 MPa. The tunnel opening is 10 meter length, and the dimensions of the model 100 meter by 110 meters. So we can run this, and when we run this, we find this interesting result that that in fact the kinetic energy of the block system around the tunnel is higher for the medium quality rocks, the GSI 60 type of rocks. That's the highest. That's why do I say that's intense? Because before we did this study, they came up with this chart, the Chinese colleagues, and they said that intense would be 4 to 7. So these are a logarithm scale. So it translates here to, oops, sorry. So it translates here to about 4. So I'll do 4 to 6. This is 6,000 kilojoule, in fact. So that's what this means, the intense. So we get the intense energy when we are in an intermediate kind of rock quality. And when the quality of the rock goes higher to 80, the intensity of the rock burst goes down. So, and also when it goes below 60. So in both cases, it goes down. So that means that the empirical classification methods can be a great input for numerical analysis to do this kind of calculations, because the engineers and the engineering geologists, they spend a lot of energy characterizing the rock mass, classifying it according to the different methods, and now we can do this kind of analysis. So to summarize, I say that empirical rock mass classification is extremely useful for both structural engineers and engineering geologists, because they provide a deep understanding of the rock mass at hand and alert for potential problems that may arise in the course of tunneling. But the critique is that empirical rock mass classification cannot, or maybe do not, address the issue of joint orientation very well. But blocky rock masses that are very common underground, in such rock masses, the relationship between the joint orientation and the free face orientation are crucial. Many times they determine the deformation mechanism. Another point is that if we want to start to go with this critical key blocks method, it's not a method. It's not a method. It was just an approach to validate block theory, but this can only be done if we basically perform a 3-dimensional geometrical analysis. It doesn't require a 3-dimensional numerical code. It's just the block theory is very, very simple. I thought maybe every operator would have something there that if they trace the joints, they will automatically generate the block and they'll know the dimension. And that was my dream when I was a PhD student, never materialized. It could have been a startup. Then the mode of deformation is very much controlled by the structure of the rock mass, and it's difficult to predict, at least to my knowledge or to my opinion, the mode of deformation for the classification methods. Rock anisotropy is a very serious issue, and it's not being dealt well with the existing classification methods. However, I showed you that some processes, dynamic processes, can be scaled. The intensity of those processes, like rock bursts, can be scaled by the classification value. So in sums, I will conclude that we need both. I think we need both. We need both empirical classifications, and I like the Q system very much. Okay, let me say that up front. So I think we need both, but we also need, of course, the numerical analysis, and we need to find a way to harmonize between those two approaches in an effective way. So this is the Tzedekah covering today. They're considering reinforcing now the roof with rock bolts, which I think is very, very wise to do, because even though the numerical method shows that it's stable, it's very marginally stable and needs to be reinforced, and they are now working on that. That's it. Thank you very much.
Okay. Thank you, Yossef. Thank you for the two presenters for these extremely interesting presentations. So we have all seen that both of you try to incorporate and use as much as possible the geological conditions, which is great. Well, before giving questions to the audience, would you like to take a few minutes to exchange between both of you, Yossef and Nick, if it is needed?
I would, yes.
Okay. Please go ahead.
So, okay, I go ahead first then. So I enjoyed very much your lecture, Yossef. I know some of these big projects also, and I've had various concerns about rock bolts and not using cable anchors, etc., that are long enough. Let me pick up one or two things where one sees differences, of course, between the numerical approach and the classification approach. I mean, I love working in teams that are doing numerical modeling. I had a couple of decades of doing that when I was at NGI, and hundreds of UDEC BB models and some 3-deck models as well. So when we have time on a big project or a big cavern, could be a dam in your case, then it's wonderful to do distinct element models. My lecture is kind of solving some of the day-to-day stuff when you're driving tunnels at 50 meters a week, even up to more than 100 meters a week in some cases. We have a record 150 meters, yeah? So you can't have the luxury of doing numerical modeling. Numerical modeling is really a luxury, and I love it when we're on a big project and we can do that sort of stuff. I pick you up on one point you made about expected failure modes, not an empirical. Actually, when one uses the Q system, we haven't had time to discuss this, but when selecting JR over JA, it is the least favorable joint set or Clayfield discontinuity. So, I mean, one is thinking about orientation, and also orientation actually comes in whether the discontinuity has a strike that is just crossing the tunnel or whether it's going subparallel to the tunnel. So your maybe lower Q value because of adverse discontinuity will apply much longer distance if the discontinuity is going subparallel with the tunnel. So I have always defended that actually orientation in effect is very much in the Q system. Maybe it's not in RMR and GSI, but it's very much in the Q system, and I use RQD in an anisotropic way as well. So we can link higher Q values with higher RQD, and very often higher velocity, higher deformation modulus, and the opposite in opposite directions. Yeah. I agree very much in making discontinuum models where the joint structures should not be just sort of crossing the page like in a carpet.
Yeah.
So it's very important to do that.
Yeah.
So always in our approach in NGI, we would get an engineering geologist, very occasionally me, to draw our impression of a representative jointing. maybe in a big drawing, yeah, and then we could move the models around in this drawing because we digitize the joint structures that are more geologically realistic rather than using these joint generators. We never do that.
Right.
And yeah, rock burst, I had one sort of question about that. I mean, I have been working a little bit with Baotang Xian, who developed the FRACOD fracture mechanics code. And his models, they show, for example, intense new fractures developing when you have intact material, which would have implicitly very high GSI, high RMR, high Q value. So there would be very strong fracturing when there is new fracturing, yeah, when there is very high stresses. And if you put some 1 or 2 joint sets into these models, the new fracturing was in some way dissipated. And also, I mean, the Jinping 1 TBM tunnels to 2 TBM or 3 TBM with a pilot, yeah, and 2 parallel drill and blast. They eventually had to go to drill and blast when the overburden was like 2.3 kilometer in the marble, which didn't have high enough strength. So you get some advantage from the disturbance with the blasting. And the TBM is in a way adverse because you get very high tangential stresses close to the tunnel wall, yeah? So I appreciate, of course, that major fractures, they're a terrible source of rock burst. But in terms of the local behavior, I would have thought that very intact rock and undisturbed rock is going to be a risk factor using TBM instead of drill and blast. So I've maybe talked for too long, so please, your turn.
Yeah, so yeah, no, I agree that in order to run those kind of numerical models, you need time. I'm going through your points one by one. So yeah, I agree that it is a luxury, and if you need to give advice as the tunneling of effort is going on, yes, then definitely there's no time, because those numerical models, not only they take a long time to generate the mesh, but they also take a very long time to run. Sure. Even with today's computers, depending on the system and the method, but even with today's computers, they take a very long time to run, and then you need to do verification and see that you're representing the rock structure correctly. So I agree, it's a luxury. Of course, if you have time, if you plan a project for another 2 years and they ask you to do the preliminary design, then I think, yeah, we should try to add to the empirical classifications also a numerical level in which we take all the input data from the engineering geologist, put it into the code, ideally we would even show them the mesh and ask the engineering geologist to approve it. Do you think this is a good representative of your concept of what's going on underground?
Very good idea.
Yes,
yeah.
And then you can run it forward. Yeah. So yeah, I agree with this point. The point about JR over JA being representative orientation. So if I understood you correctly, what you say is that you basically try to select the worst joint set and then apply it.
Right.
Yeah, so I see. So yeah, that could be a way to handle that. And I'm happy that you agreed with my point about the meshes, that people are drawing straight lines.
Yeah, it's incredible.
I did this. In fact, my first project with DDA was on Masada, and I started modeling the mountain with lines, and everything collapsed. I mean, I was the first to introduce an earthquake to DDA, and everything collapsed. Nothing stayed. And of course, it's not collapsing. Masada is standing till today. Once we started, in fact, what we did then was digitize, as you said, digitize the lines. We drew a map from with a tracing paper on the photograph that was taken from a helicopter, traced the lines and digitized them into the DDA, and then let it cut the blocks, and then it was more.
No, that's the way. I mean, there's another help as well as having non-continuous joints. If you have BB parameters, I mean, I'm biased, of course, but JRC, JCS is going to give you the development of dilation and sometimes self-stabilization.
Yeah, right.
Whereas if you had low friction without dilation, you may get collapse. Yeah. So for me, I'm very biased concerning Q and BB. So we like to have roughness in the models. Yeah.
Yeah. And that digitization of the lines provides a roughness in the outcrop scale. It gives you, because in the model we give the joint a friction angle. But if you generate a realistic mesh, then you got a roughness in the model domain, and that will mobilize more friction, will be more stable, will be more realistic. So we agree.
But not just friction, we need dilation. Dilation is very important that that's modeled, and it's obviously central in the BB model, and maybe not so sophisticated in more Coulomb. It's kind of a ramping bilinear, and a significant difference between bilinear ramping and slightly S-shaped in the BB band is found. There's significant difference.
Yeah.
So you can get sort of kink bands with a BB model, UDEC BB, but you don't get kink bands. You just get an individual failure area, in the more Coulomb.
That would be. No, that would be one of the challenges for the discrete element modeling community, to implement a roughness profile the way you presented them, or some other kind of presentation, but to consider actual roughness in the joints themselves. That's nobody has reached that level yet.
But I mean, it's in the BB model, but because of the constitutive laws, right? I mean, dilation is actually occurring with deformation based on the JRC mobilized, it's called. And this worries me about wedge analyses, unwedge. I mean, you can change the friction angle, but I'm not sure that I've seen dilation, and definitely I haven't seen tangential clamping of wedges.
So
people come up with extraordinary geometries of wedges that are never going to fail. And,
I agree.
It worries me a bit to see these.
I agree with you. I don't. We have it in the class to show the students to practice with it, but I agree. I don't. Personally, I don't.
I once saw a wedge 42 meters high, and the people were not really understanding it. They're wondering if they could select long enough cables to keep this wedge from falling. And I mean, obviously, it just gets clamped.
Right. For sure. And about the rock bursts, so it goes two ways. If you have joints and they're oriented in a way that permits, kinematically permissible, to move out of the rock mass into the space, then I think that it will be much easier once this energy is being released because of the excavation to have those blocks slide on pre-existing joints rather than fracture the rock from the beginning. And so most of the seismic energy comes from that. But if you have joints that are not favorable for kinematically, they don't have the right dip, they say dip into the rock, then you will have fracturing of the rock, and the other joints in the area may assist in dissipating the energy by sliding and stuff like that and drain the blast.
I mean, in Jinping 1, the marble was just not strong enough in relation to the tangential stress.
2.5 kilometers, and the strength of the marble there is only 60 or something MPa, if I remember.
Or up to 110 maybe, but still not high enough.
Yeah, I agree.
So they were asking for problems there. I mean, poor people, they had to do it, and they got through, and they've even got laboratories, rock mechanics laboratories adjacent to the tunnels, which is amazing. And his people, they have nice research going on there at nearly 2.25 kilometers depth.
Okay, thank you again, Yossef and Nick. I think this is time now to ask questions coming from the audience. And I have one question from Senhu. Yes? Okay.
You're mute.
I'll read the question. I identify 3 factors that may restrict each approach, numerical or empirical. A, the extreme overburdens. B, the dimension of an excavation. C, reliability amount of available information data. How these factors could deviate design and even construction efficiency, an empirical or in numerical method. who is going
extreme cover and span, and what else was it?
Extreme overburdens, dimension of the excavation, and 3, reliability amount of available information, data.
That one I'm not catching, the last one. Say a little
Last
bit
one,
more slowly.
reliability and amount of available investigation data.
Okay, sure.
Where basically the geological
Yeah.
input
Yeah.
Sure.
coming from the investigation.
So, Nick, you want to go first?
This was addressed to whether our respective methods,
both,
I mean, we
I don't
both
know,
use
to
the same
both of you.
methods sometimes, but whether our respective methods could address those extremes. I mean, we have used the Q system down to like 2 kilometer depth with obviously very unfavorable stress to strength ratios. Actually, now we should think about tensile strength divided by Poisson ratio for predicting the possibility of the rock burst. The span dimensions, I mean, the Q database is, let's say it's from 2 or 3 meter up to 60 meter span, and have 1 or 2 up to more than 100 meter, but it's from natural caverns, yeah, and limestone. So I don't think the dimension is a limit there. The data is always a limit for everybody, and we have to do some creative constructions like Yossef was showing, where we estimate possible structures from using experience, yeah, and with an imagined range of GSI or RMR or Q and so on. So if there's not the data, we have to use experience to create the data. Otherwise, go out and do some drilling and seismic refraction, yeah? If it's too deep, you can't do that. So you have to you anticipate conditions from having visited these deep mines, or if that's the objective.
Yeah, I'll pick up on this last point that it's very difficult to convince the owners to invest more in site investigation. And then we're limited. All of the analysis, all of the design is constrained by 1 or 2 boreholes that are budgeting, especially if these are transportation tunnels and they don't have much excavation or time. And I think the engineers and the engineering geologists should insist and not compromise to have as much exposure as possible in advance to avoid catastrophes, especially in caustic cover situations. We have in Jerusalem Hills, we have caustic problems a lot. And those things could be missed if the boreholes are too far from one another and they're not representing the rock mass properly. About the depth and the span, yeah, that goes into the model. The depth goes in terms of the stresses that we impose. We don't model the entire mountain because no computer can do that. We calculate the stresses at the point of the excavation. Then we generate a model around the tunnel and we impose those initial stresses on the boundaries of the model and let it run. And we use non-reflective boundaries and stuff like that in order, instead of modeling the entire mountain. And of course, the span, we showed in those cases how the span is significant. Both Nick and I have shown that.
Okay. Senhu, you have a question.
Yeah, it's like, yeah, I have one question. So I just would like to ask you, first of all, it's Sen who gave me permission to enter to ISRM entrance. So my name is Dmitry Olshansky, but doesn't matter. So
okay.
Doesn't matter. Dmitry Olshansky, Yossef Hatzor. אנחנו מכירים בעצם. Doesn't matter.
Oh, yeah? Oh, okay.
Yes. So I just like to ask a question regarding ISRM. So we have 3 books, ISRM 1970, Yellow Books and Blue Book. And then the 3rd book was issued maybe 7 years ago. My question to you, and this one I was surprised, in first 2 books, we have very good chapters for outcrops, how to describe all joints and fractures and et cetera, from geological point of view. All of a sudden, all these chapters disappeared and people just was concentrated on just lab tests and borehole log scores. Actually, and what I'm struggling every time, I'm from Canada, okay? I'm living in Canada right now. So I was surprised how come the most important chapters was disappeared from ISRM book because I'm just struggling. I'm geological engineer, yes, and geotechnical, doesn't matter, slash. So I'm struggling every time with civil engineers, so like tunnel engineers and etc. They couldn't understand, we can do everything based on borehole core logs or something. You guys, forget about that. The best experience, outcrops or description from tunnel, all joints. You cannot do anything from cores, especially most of cores, by the way, this one another story, because when I studied in university, I just learned how to do structural, like inclined boreholes. I've never ever seen in my life, after 30 years working in industry, like inclined, like very rare, when you want twice. That means most of boreholes are vertical. So definitely, and people, by the way, trying to describe all description based on core. Guys, you cannot make strike and dips because your core rotated inside your drilling. And people cannot get it. And all chapters was disappeared. I was just freaked out. I'm sorry for like my language, but it's what Yossef, by the way, like I just tried to do like long time ago, 30 years ago. Do you remember me? Maybe younger. I just would like to do with you a PhD, but doesn't matter. Then I just it was 30 years ago, 1991, something like that. Doesn't matter. Okay, so
I think to answer your point, I think those Nick was involved in the ISRM suggested methods for the classification of rock mass structure. It's a beautiful chapter, and if it doesn't appear in the modern version, maybe because they decided to keep it as it is and not to change it.
Mm-hmm. But
they are trying to. There's a group that is trying to update it.
Yeah. The issue is people cannot understand all gaps, opening, filling. You can do on Teleview acoustics. That means you something to have some electronic equipment inside boreholes or based outcrops, and like they make up all these Hook-Brown parameters, GSI, and etc. based on just boreholes, which actually almost impossible. And I cannot, because right now in third edition, we don't have this option. Every time I'm just keeping this book, I'm so happy I have this book. So every time I just scanning, I'm sending and explaining approaches, how you have to look at all parameters, because geological point of view.
Okay. I have another question from
can I just make a quick comment about the core?
Oh, yes.
If the core drilling is done, let's say in a very intelligent way, with some knowledge of the structure, then you can get very useful information from core drilling. I remember some years ago, I was involved actually in a tunnel where you've seen some pictures in my lecture, where for this 5-kilometer tunnel, they had a lot of folded and vertical structure and vertical volcanic dikes, which were a big problem. So basically the coring was like 400-meter long, 20-degree from horizontal inclined boreholes, and along the length of the tunnel, covering a certain amount of the tunnel, And this was very useful because it crossed all the structure. And it did give, I did the Q-logging of all those cores and also looked at the permeability and the P-wave velocity near the surface, and it gave good correspondence with the tunnel conditions. So sometimes if the drilling is in the right direction, you can get good information. Otherwise, you may not, I agree. Okay, please, next one.
Philippe, may I say something on behalf of the Commission on Testing Methods? I'd just like to answer the previous comments. The Commission issued the Blue Book, and it issued afterwards the Orange Book. The Orange Book includes all the suggested methods that were published after the Blue Book was issued. So all suggested methods that are included in the Blue Book and in the Orange Book are available to everyone nowadays. So continue using the Blue Book, and if you want to use the suggested methods from the Orange Book, it's okay. And as Nick Barton said, there is a working group working now to revise the the old suggested method for the description of discontinuities in rock masses. That's just I wanted to say on behalf of the Commission on Testing Methods. Thank you.
Okay, thank you, Yossef. Another question: can a numerical approach address large to medium scale uniformity?
Yeah, that's a difficult one to understand. Uniformity meaning from isotropic towards anisotropic, or what?
Probably, I don't know.
It's not easy to, it has to be defined a bit better to answer that, I think.
Yeah. Okay, I have another point to ask you more specifically to you, Nick. It is written, Shomo Lieberman. I want to ask, why do you say the Barton method is, the Q system, is much better than GSI method? Do you mean that the GSI method is more risky and that tunnels may fail using this GSI method?
Yeah, well, we should have a separate debate on this. And I know there are a lot of young and not so young people who love GSI. They felt that, I read in one of the articles, that finally the geology is represented because of GSI. And this was as if the Q and RMR used the last 40 years were not addressing the geology at all, which of course is nonsense, yeah? So for me, I don't think GSI is in any way comparable in relation to being empirically derived. It's actually derived by modification of a very good empirical criterion for intact rock, the Hook-Brown criterion for intact rock, back from the 1980s, I guess. Those classic books of Hook and Brown, yeah, and Hook and Bray before, of course. So for me, GSI is difficult to really apply in a realistic way over a big range of conditions. And there are lots of attempts to improve the quantification of GSI. And the equations for C and phi of Hook-Brown, they look very impressive in the rock science curved failure envelopes, but it's not really empirical. It's guessing. And when these methods have been applied, the GSI, Hook-Brown, and the Fein-Zermatt model, there's evidence from a formal court case with a lot of experts that the plastic zones are grossly exaggerated in relation to reality against a real tunnel, yeah? And the spoon-shaped failures that people are predicting using GSI-based improvements in the more Coulomb parameters, the spoon-shaped failures you don't get in open pit slopes, actually. They fail because of interaction of joints and major discontinuities. The spoon shape is wonderful for soil and maybe rock fill, maybe very, very weak rock, but not for competent rock more than a few megapascal strength. So I feel that there's a lot of misrepresentation with GSI and Hook-Brown.
I think that GSI personally is rather widely used simply because of the images. As Yossef said during his presentation, we can catch the images and see, well, if they represent or not what we are facing when looking to an outcrop. However, this advantage can be also a disadvantage because it is simplifying the geological, or even oversimplifying the geological reality.
We need a million images.
Of course. So it can be useful, but will never cover all the geological situations. Well,
I think, if I may, I think the problem is the attempt to carry it over to predicting rock mechanical properties like Young's modulus, and that's I think attracts most of the criticism. The table itself with the structure and the condition of the joints, I think it makes a lot of sense with the pictures and the graphs.
Yes.
But the attempt to take those numbers and then force them into predicting the rock mass strength and rock mass elasticity, so we end up with those equations that Nick pointed out that are not feasible. Nobody's going to be using such equations to predict. We all know that it's empirical anyhow, so why use such long? So that's maybe they went a step too far, because Hook and Brown themselves said that about the Hook and Brown criterion that they didn't intend this to be something very accurate. It was more like scaling, and now they take the GSI and use it to predict strength, deformability, and that may be extending it too much, too far.
Yeah.
I mean, the problem is that GSI and Hook Brown, they end up in a mixer, and you get a continuum model. So where's the geology in the continuum model?
It goes away.
It goes away. Yeah, it's fluids of different viscosity.
I just would like to step in, just ask one more question, guys. How applicable all GSI and other models, constitutive models, because we have real rocks like limestone, dolostone, some basalt, etc., and we have half rocks such as shale, chalk, marl. And what I found, because here in Canada, in Toronto, for example, we have shales, okay, and everyone using GSI models and etc., Hook Brown, etc. How applicable is that? Because like every time when we're drilling, it's like, because of half rock, I don't consider it's rock, it's real rock. It's kind of compressed soils whatsoever. Yes, more cemented, less cemented, but it's not rock. And generally, most of joints or bedding or whatsoever horizontals in this type of shales, type of rocks. How applicable, or what you think the best model for this type of materials, shales, chalk, and marl? I just would like to ask you.
I mean, your shales, for sure, they are too anisotropic, really, to be represented in GSI. I mean, I don't think Hook wanted GSI to be used in anisotropic conditions, but later Marinos joined him and came up with some more sketches with very anisotropic flysch and things like that. Really, to my mind, going a little bit outside the original intentions of GSI. Because GSI, I mean, Hook has thought of GSI as an isotropic property, and RMR as isotropic. He thought Q was isotropic also, but it's not. We use it in a very anisotropic way. So when you have the really anisotropic rocks like your shales with the high horizontal stresses as well, I don't think you're going to get representative results with GSI-based methods. Chalk, I mean, depend on the strength of the chalk, of course. I've shown that the Q system can be used way down to just a few megapascal strength. If a rock mass is jointed, we can use Q even if the strength is very low, and we mobilize UCS over stress or tensile strength Poisson ratio to see if there's a fracturing problem. Yeah. But things like, what's it called, lahar, the volcanic ash that's been transported and deposited and is almost without joints, we can't tackle that for sure with RMR and Q in a very realistic way. When there's no joints, it's difficult to use these methods, yeah? And you have to, it's a continuum you're looking at, you have to use a continuum method in some way and get appropriate input data.
Thank you, Nick. I see that Luis Lamas has raised his hand. Luis, you have a question?
No, I don't have a question. I just wanted to make the same clarification that José did. I made about Senhu's comments about there's the blue book and the new book, the orange book. But José Morales already clarified everything. So they are complementary. They complement each other. They don't replace each other. That's what I wanted to say.
Okay, thank you, Luis.
And congratulations for the excellent debate.
One question from Christoph Weber from Switzerland.
Can you hear me?
Yes.
Yes.
Yes, my question was about particular cases relative to the mudstone or siltstone that, and specifically in the case of water tunnels, I have seen several cases of failure of water tunnels because most probably well, when you excavate, it is in dry condition. Then when you fill up the tunnel, it will be under wet conditions. There will be variation of pressure in the tunnel, then modifications in the geotechnical characteristics of the joints and maybe also on the matrix. And I would like to know what would be the best to represent that. I think in myself that the most representative that I have seen is the ISRF and the Q system. But most of the time, in the failures that I have seen, the Q system was used to define the final lining, and most of the time the failure was because the people did not apply correctly SRS. So this is mostly how could we improve to avoid such phenomena. And with regard to modeling, this I do not know any other methods than to take very conservative parameters in order to anticipate this phenomenon. But how would you treat this problem?
Yeah, that's very good question. The water tunnels. Incidentally, for those that don't know, the majority of the original case records for developing the Q system were actually hydropower tunnels from Norway and Sweden. So a lot of hydropower tunnels with slow flowing water, say 1.5 to 2.5 meter per second. And one problem I've seen, I'll come to the Madstone in a moment, but one problem I've seen is that sometimes people have used an unchanged Q logging to design supposedly the support for a river diversion tunnel with very high velocities. And there's been an enormous failure because of that in Colombia, yeah, where the velocities were more than 10, 12 meters per second, also going around a sharp bend. So the people have not thought about the forces involved and the erosion and so on. So, of course, mudstones, they have to be very carefully protected with shotcrete, continuous, going around the invert. And one little item is to imagine the future condition of the tunnel, the future use of the tunnel. So when evaluating JW, you mustn't use 1.0 in the future water tunnel, yeah, even if it looks very dry, because there will be some leakage through the shotcrete, the changes of water pressure, the dynamic effects of the hydropower operation. They will cause water to get into that rock mass, even if it's not there at the time. It may have been sucked out by capillarity when you're observing it anyway. So great care with protection of the weaker rocks all around the invert. None of these bad conditions, poorly prepared tunnels at the bottom of the walls. And fiber reinforced shotcrete, of course, to give the very low permeability. Not use mesh reinforced, which invites corrosion because of electrolytic corrosion, the continuous steel. Yeah. So there are some major failures in a few hydropower tunnels due to incorrect use of Q. I know some projects, I'm sure you do, of some enormous number of failures where people had no understanding of using Q. If it's used correctly, you can get thousands and thousands of kilometers of trouble-free water tunnels.
Yeah, so what I suspect most of the time is also that what is observed actually is that in pressure tunnels lined with only with shotcrete in this kind of rock, the cracks are unavoidable. So it's unavoidable that you have, during the operation of the tunnel, circulation of water into such rock. Usually the infillings are slightly erosive or softening. And this is, in my opinion, one of the main causes.
But I mean, are you proposing using steel reinforced concrete when you go through these soft rocks?
Yes. Yes.
Okay.
In such
quite
weak
conservative,
rocks. Yes. In order to decrease the permeability of the lining and to avoid the water under pressure to penetrate.
But I mean, you don't prevent cracking with steel reinforced concrete either. You can you can get fluid into the rock also, but it's less of a lesser degree. That's true.
Yeah, you can support more load also.
Yeah.
But in GSI, for instance, for me, is not in that case. Is not of good use.
No, it's not got the right parameters. Yeah. Thank you for the question.
I have one thing to ask you, Yossef. In the case you have good geological data, input data, and enough geological data, which is good. How do you manage this when preparing and building your model? Because too many data means something difficult regarding the model and also difficult for the running time. So how do you make the exercise, the balance between the reality and the model itself?
It's a great question. So yeah, we need to be able to put the data into order. For example, if they mapped the joints, and did a joint survey, we have to insist to plot the results on stereographic projection so that we can identify the major joint sets. And for each joint set, we need to find the representative mean orientation. The same we need to do with the spacing. We have to do all the bias corrections and find the mean spacing. Length and bridge are things that are a little bit more sophisticated, and you need an outcrop anyways to define them. So we can exercise engineering judgment, but we must have a good picture of the main players in the game, the main joint sets. Each joint set, we need the geologist to tell us, is this a shear? Is this a tension fracture? Is this a fault system? And they should be systems. In geology, they go by systems. If we don't make order at this stage of the site investigation, we're going to get a mess. So now, once we know exactly that we have 2 or 3 major joint sets, and we know each one what's its origin. One is joints, tensile fractures. One is shears. The other is faults. And we give them, characteristics: low friction, high friction, low roughness, high roughness. Then we have enough tools to, and we need to know, the distribution of the spacing, if possible, and if not, at least the mean spacing. And then we have enough tools to select the critical, the most dominant faults, discontinuities in the system, and to generate it. We would not like to do it one by one. We generate using a line generator, but this line generated code can accept various lengths, various spacing, various bridges, and then we examine the mesh that we obtain, and we ask ourselves and consult with everybody involved in the project, is this representative of the problem? Once there is an agreement, we can run the model forward. It would be a waste of time to run the model without establishing first the correct mesh. So that's very, very much linked to the site investigations. And the friction is important, friction can be very different between joint sets, and that will have a very important effect on the deformation. So we need to, people don't send the samples for direct shear testing. I don't understand this. They do only uniaxial compression. Why? Why aren't they testing direct shear? I mean, I'm talking about my country. They don't.
Mhm.
And it's very important. Nick mentioned the issue of roughness, of course, and dilation. All of these things are very important to define the correct friction. If we can assign a friction angle with confidence of 55 degrees for a joint set, then it's going to be a totally different picture than if we assign a friction angle of 20 or 15 degrees.
Mhm.
We don't want to be extra conservative because everything then will collapse. We
In one
need,
of, yeah,
we need to
excuse me.
represent.
In one of our big projects, we were responsible for logging like 10 or 11 kilometers of core, and we took hundreds and hundreds of samples, maybe 50 or so for direct shear tests, but hundreds and hundreds, maybe up towards 1,000 for tilt tests and Schmidt-Hammer tests. So you get a very nice representation of JRC from tilt tests. You just need a diamond saw to cut samples, so you have sort of slender upper samples. Yeah.
Yeah, the
You can
advantage,
extrapolate.
the advantage of the JRC and JCS as the two parameters that you can actually establish almost in the field without having to ship samples to the lab. That's a great advantage of the Q system.
Sure.
Yeah,
Mhm.
for sure.
So,
Yeah.
Yossef, you insist, in fact, on the team working.
Oh,
The
definitely.
collaboration between the field geologists and the modelers.
Definitely. I
Yes.
think if you let the models run, what modelers run wild, they have no understanding what's going on in the field. They will just run models. So there has to be, so the manager of the project should be able to tie those people together and have a
Okay.
close discussion between the two.
Mhm. I have a last question, and then we will end this debate. The question is, Professor Hatzor mentioned karstic phenomena. I believe it is relatively easy to insert a cavity into a DDA mesh. I would like to ask, what would be the best approach for the Q system to handle karstic cavities? Would that be increasing SRF or maybe multiplying JN by 2, whatever? I don't know.
I'm sorry, I got a bit
So how to incorporate?
distracted. I got distracted by messages that are coming on the screen of other questions.
Just
Could you
resuming
repeat
the
the first
situation.
part?
How to insert karst or karstic cavities in the Q system? Would you increase the
Depends how
SRF or
large they are.
multiply JN? Well,
yeah, I mean, it depends how large they are. I mean, some karstic cavities, your TBM comes to a void, and the next few months is involved in making a bridge across the cavity so the TBM can get to the other side. But you have to do conventional blasting to get the tunnel started again before the TBM can continue. So, I mean, that question is very much depending on the distribution and the size distribution of the karst.
yes, especially the
Whether or not
type
it
of
fits in
karst
the
and
system
size.
at all, because I mean, Q is 0 in air, I suppose, and some of the karst is air. And what's the porosity in average, and what is the size distribution of the karstic cavities? So it's many complicated things in
Yes.
that interesting question. Yeah.
You're right, Nick, because people say karst, but the karst covers a wide amount of situation, very different situations.
Yeah.
Yes. Well, I think this is time. I'm sorry for the other questions, but people can even contact directly our two presenters just in case, if they want some additional question, results, or comments. Thank you very much, Nick. Thank you very much, Yossef, for these very interesting and very useful presentations. And that has been a real pleasure to manage this debate. Thank you, both of you.
Can I
Leandro?
just ask you one thing, and thank you as well, Philippe?
Yeah, Philippe, thank you very much.
Quite a lot of questions have come on the screen because people have just typed them in. Are you keeping a list of that, and can we see those questions? Because in principle, we could send emails or to yourself, perhaps, and you can contact them. Yeah, it's a pity for those questions to be lost.
You know,
Okay, I can record this question and send it
Okay,
to.
that's
okay.
good.
Yes.
Thank you, Leandro.
Okay, this is the best way.
Thank you for a very nice arrangement. I guess we had plenty to talk about, yeah?
Philippe, could I give you a suggestion for the next debate?
Yes, of course, Ida.
Thank you. To include water. Some years ago, Professor Brown, Ted Brown, told it seems in his Muir lecture, he told it seems that every rock mass is a dry, let's say. And then one very important thing in rock mass excavation is water. And it is so difficult, this approach, this question, that this is never included in discussion of modeling. There is partial modeling to consider water, but it is very difficult to include water in the modeling because of the difficulties. There needs a lot of excavations, needs explicit testing. And I think a debate, European debate on this would answer many questions. Professor Christoph Wiebert is here, and he knows the difficulties. Everybody that has been working with water feels how to interpret it, how to put this in modeling when it's most of models just dry. That's my suggestion. Very good debate, wonderful debate, very nice.
Ida, thank you very much, because this is a very good suggestion. We all know the impact of water and the effects, very often detrimental effects of water in rock masses. But it is difficult to investigate first, and it is also difficult to model these effects of water. A debate on that would be something very interesting for our community. Yes, I keep it in mind, Eda. But give me some time.
It's already difficult to convince owners to make comprehensive tests on dry samples and on saturated samples. And it is a difference.
Yes. Leandro?
Okay, with all this, I thank you all attendants and the speaker and the moderator for being here today. And we'll try to organize another one of these debates in a few months. Thank you for being here. With that, I close this third debate, European rock mechanics debate.
Thank you very much, everybody.
Thank you. Bye-bye.
Thank you. Bye-bye.
Bye.
Pleasure. Bye-bye.
Bye-bye.
Bye.
Leandro?
Hi. Yeah, I'm recording the last questions, and I will send them to you so you can send them to this people.
Okay.
Okay. I think it was a very good debate.
I think so. This kind of debate with two people like Nick and Yossef could last hours. Of
yeah,
course.
I know. Yeah, but yeah, it should be close at some point.
Okay. Yes.
Okay, keep in touch, and I will.
Okay, we keep in touch. I have one or two proposals for new debates to suggest for the future.